Hello everyone. In this video we're going to be taking a look at exponential modeling. So in this case we're given downloads versus months, whereas to create both an exponential and a linear model, and then we're going to analyze it with a little follow-up question on the end. So the first thing, if we're going to be creating models, we have to understand what each of these look like in their kind of generic form. Exponential functions we define as a times b to the x power, such that a is some initial value. Graphically, we know this is the y-intercept, or where x equals 0. Times b to the x power, that part is we can refer to it a few different things. I usually like to call it the common multiplier. Some other places might use words like ratio or something. In other words, what are you multiplying by from term to term? As x increases by 1, what's the common ratio that you're multiplying by? For linear functions, this is what we started the year off with, and many of you learned this in years past, mx plus b, where we define m as the slope or rate of change, and b is our initial y-intercept value. Once again, where x equals 0. Now this can be a little tricky looking at both of these together, because notice they both use a b and it both means drastically different things. So this can be a little tricky. We want to make sure we understand how these work before obviously we start building something. So now that we have those down, let's go back to the actual data that we have here. So we have 2 months, there's 2,000 downloads, and after 4 months there's 3,125. So I'm just going to record those as kind of points here. 4, 31, 25. So I'm going to start with exponential. And it's pretty clear that this isn't an obvious multiplier. It's not something like doubled or tripled that I could see in my head. So what I'm actually doing on my calculator right now is dividing. When I divide 3125 by 2000, it will tell me what I multiplied by. Just like if you divide 16 by 8, it will tell you that you that you multiplied by 2. So I divided to figure it out. That was times 1.5625, which obviously, like we said earlier, I don't think anyone will look at that and pick that out right away. Now, this is a little bit of a trick that comes into play. Most people would kind of plug this in for b, as is. That's actually incorrect. Take a moment to see if you could figure out why. It has to do with, and why I purposely left a little space here, this was really 2 jumps. This was really 2 things being multiplied back to back, the same number obviously. So we still don't know what b is. So this was times b, this was times b again. We know that when we did it 2 times in a row, which isn't 2b but b squared, we get this 1.5625. I know b times b again is 1.5625, which does help me, believe it or not, because I could solve this using square roots. We're going to assume that b is positive here. So we're going to ignore the negative result of this radical. So we take the square root, obviously, on our calculator. That's a really ugly square root, sorry. Square root of 1.5625, make sure it's all under the radical, is a nice 1.25. So just pay attention to stuff. It's nothing that you can kind of say, oh, this always happens. You know, every problem is different, but just be aware the common multiplier is between consecutive terms. Okay, so we know b, great. So our function's kind of halfway built right now. We still are missing the initial value. And remember, that's our y-intercept. Sometimes initial value can be used in the same way that y-intercept can. So we can do something for that. Kind of related to what we just did. We could work backwards. If I want to know what the y-intercept was, where x equals 0, I know that it's 1.25. I can work backwards. I could divide by 1.25 twice. So I'm going to take 2,000. I'm going to divide by 1.25. I get 1,600. And I'm going to do it again. And I get 1,280. Remember, we're dividing here because we're undoing the multiplication that really took place going forward. So I know my b value. I now know the y-intercept is 1280. My function is determined. It didn't say what to call this. We'll call it f of x. Always make sure to see if you're told to call it something, you want to call it that thing. 1.25 to the x power. Leave it like this. We can't do the multiplication there, obviously. That's our exponential model. An alternative to this, which would be very creative, if not lazy, because it's actually doing less work. You still need to find the 1.25, but you can do that with your exponent. Now what this is doing is saving you finding the y-intercept, because now you could just use that value, your kind of fake initial value from the table of 2000. And you can check this. These are the same function. Think about why it works. If I plug in a 2 for x, it's going to treat, like I said, kind of a fake initial value. It's going to create an output of 1.25 to the 0 power, which is just 1, times 2000. So it gives me the values in the table accurately. What it's really doing is kind of like sliding the graph over to fit. And this does work out the exact same, a little bit more creative, knowing your exponent rules and how you can manipulate exponents. Both of those would be sufficient to model this data. We also call that in class an adjustment function, kind of making an adjustment to fit the given data. And now the easier of the two, the linear model. So now I'm going to copy the points again. This should be very quick. 2, 2000, 4, 3125. Okay, so for linear, we're going to start with slope, delta y over delta x. What's the change in x? And the corresponding change in y. That's going to tell me my slope. So the change in y here, you can do even without a calculator. It looks like it's 1125. At the same time, x increases by 2. Now this is going to be a decimal. We could leave it as an input. Okay, so that's my m value. Now I could work backwards, similar to what I did with the exponential. I could subtract, not divide, because remember with linear we're adding the slope over and over again. I could subtract 562.5 2 times in a row to give me the value at 1 and then the value at 0. You could do some solving to solve for b. Let's do the subtraction. So at 1, if I do 2000 minus this 562.5, I get 1437. And then at 0, 1437. I get 875. Okay, so I know my b value is 875. Once again, this function is determined. I know m and b. So let's call this g of x, I suppose. We have 562.5x plus 875. An alternative that we didn't talk about, depending how this would be phrased with showing your work, we could obviously use regressions using the appropriate one, exponential regression on the left and linear regression on the right. That would be using the stat feature, edit, using L1 and L2. You could actually just keep those values in there. You would type in 2 and 4 for L1 and 2000 and 3125 for L2. Then stat calc for lin reg, choice 4. For exponential, you got to slide all the way down to choice 0, exp reg. Good way to check, or like I said, if you're really stuck, you could use those. And now the last part, we just want to, when does each one predict over 10,000 downloads? So this is going to be using the calculator. When is this over 10,000? And when is this over 10,000? Okay. And right now I'm just typing them in. You could type both in at the same time. To the x power and 562.5 x plus 875. So for f of x, keep scrolling here, we see in month 9 it's 9536, and then month 10 it's 11,000. So month 10, I suppose, is the first one where it's over. And for the linear, this is going to grow a little bit more slowly. It's over 10,000 at week 17, or month 17, excuse me. Okay, so this is exponential and linear modeling in one problem, knowing the basic foundations of how these functions are set up, and then being a little bit creative with how you find missing information. There are always alternatives. I mentioned a few, but I actually only did one, obviously. I divided to find the initial value over here. I subtracted to find the initial value here. There's a lot of other ways to do those. You can make adjustments, like I mentioned. You could also do that for the linear. And that's everything. So thank you for watching, and hopefully this helps with your exponential modeling concerns.